In this video we're going to consider distribution of sample means for random variables which aren't themselves normally distributed. So far we've sort of said, well, if the original variable is normally distributed and we consider the means of samples taken from that, then we'd expect the distribution of those means to also be normally distributed. So let me start with a statement and then I'll try and explain what I mean by that. So for a random variable x, with mean mu and standard deviation sigma, and we're saying that this doesn't have to be normally distributed itself, if the sample selected is large enough, and the syllabus gives us a specific number here, so n is greater than or equal to 30, so if our sample size is at least 30, then the sample means, x bar, the mean of any sample, is approximately normally distributed with mean equal to mu and standard deviation equal to sigma on n. Now we've already seen these two here, but that was sort of when we were talking about variables x which were normally distributed. So let me try and explain what this statement here is saying. Think of maybe a couple of other possible types of distributions that we could get. So something like a uniform distribution. So, you know, the kind of thing that happens when you roll a dice or something, you expect that you get the same of, the same number of each type of outcomes. That's a uniform distribution. Think of another one that we've considered not that long ago in specialist maths, which was an exponential probability distribution, so something shaped like that. Now, if you were to take a sample of values from any of those distributions, if the sample was large enough, and you were to study the distribution of that sample, what you would expect is that the sample itself would, model that pretty accurately. That's what we'd hope. If we get a random sample that's big enough, then we'd expect that it's going to sort of model this pretty well. So same mean as these, same kind of standard deviation. But what this is saying is, or this statement here is saying is, again, if we take samples of, size at least 30 from here, so n greater than or equal to 30, and we keep taking samples of that sort of size from here, and we looked at the, the x bar value, the mean from each of those samples, then when we studied that distribution of all of those there, they would be approximately normally distributed, the means themselves. And I think that makes intuitive sense if you think about it. If we're just considering the averages themselves, then we would expect the averages themselves are going to be pretty close to that, and there's not going to be that much variation, and any variation that does occur is going to occur in a sort of normally distributed type fashion. So bunched close to the mean, and probably sort of equally both sides of the mean. The further we get away from the mean, the less values we have. So really all this statement here is saying is that what we already knew to be true of sample means from normally distributed variables is actually true for sample means from any random variables, regardless of their type of distribution. And so that's a pretty significant thing that actually means we can use this for a whole lot of other situations as well. So let's remember a few things that we know about distribution so that we can calculate means and standard deviation. So I'll put this under the heading recall. Recall that for any continuous, and this doesn't need to be normally distributed, but for any continuous x, so random variable x, with a PDF, so probability density or distribution function of f of x, which is defined or valid between values of a and b, that the mean of those, or the expected value, we can find using integration. It's going to be the integral, definite integral between a and b of x times f of x dx. Okay, and we can calculate the variation, or the variance rather, in x, and we know that the standard deviation is just the square root of the variance. So the variance of x is going to be, well, we can actually do it with an integral, but I think it's better for us to remember this one here, which is that it's the expected value of x squared minus the square of the thing we just mentioned above, so the square of the mean. Okay, so expected value of x squared minus the square of this value we would have calculated. And e of x squared is just where we replace x with x squared there. So let me say that here, where e of x squared, the expected value of x squared, is just going to be x squared times f of x in the integrand. Okay, that was for continuous. What about for discrete variable x? So if I had a discrete variable x, then I could say that e of x is going to be equal to, remember this time we multiply each of the individual probabilities by or each of the individual outcomes by the probability of them occurring. So it looks like that, where this represents the outcome and this represents the probability. So it would be like the one where we had maybe a die rolling 1 to 6. So we'd say the probability of rolling a 1 times 1, the probability of rolling a 2 times a 2, and so on. And specifically for binomial, so for a binomial variable x, we can say that mu is equal to n times p. So remember, a binomial is a situation where you do n trials and each trial has the same probability of success or failure, and sigma is equal to the square root of np times q, or times 1 minus p. Now some of those formulas are on your maths methods formula sheet, but they are not on your specialist maths formula sheet. Right, let's consider a specific question here from 15E, where the distribution is not a normal distribution. In fact, this one's a uniform distribution. So the lengths of blocks of cheese, x centimeters, produced by a machine have a distribution with the PDF as shown here. So f of x is equal to 5 if x is between 10 and 10.2, and equal to 0 otherwise. So just quickly, that would look something like, let's maybe put a little break in our axes there and say, okay, here's 5, here's 10, and there's 10.2, and so between those two values of x, so the distribution is uniform between those two values and 0 everywhere else. It's uniformly 5 between those two values. We want to find the probability that a randomly selected block is more than 10.1 centimeters long, and then find the probability that the average length of 30 randomly selected blocks is more than 10.12. There's that magic sample size of 30. So once the sample size is 30, we can assume that the sample mean is normally distributed. Okay. So first of all, we're just saying, what's the probability that if I select a block at random, what's it saying? It's going to be greater than 10.1. Now, I don't know if you can look at this and almost intuitively see that 10.1, since that's going to be right smack bang in the middle, that is presumably going to be the average. And so the first question is really just saying, what's this probability or area here, which we'd expect to be 1/2. If we were going to calculate that, because we weren't too sure, then we'd be saying what the area between 10.1 and 10.2 of the function y equals 5 with respect to x. Now you can do a little bit of, let's go 5x, 10.1 to 10.2. So you can do some calculating there. And indeed, that will come out to be 0.5. That's that probability. All right, so it's part B that we need to do a little bit more working out. So in part B, find the probability that the average length of 30 randomly selected blocks is more than 10.12. We'll look again here you could almost say, without doing any working out, that you know the average is 10.1. But because that's not always possible, let me go through some working out. So the expected value of x, which is going to be the same as the expected value of x bar, is going to be equal to 10.1, 10.2. Remember, it's x times f of x, so x times 5 dx. If you grab your, here we go, let's do it. Now, I mean, we could easily do that tech free, but because at some point during this question it's probably going to become tech active, let's grab our calculator and, actually work this out. So what have we got? We want a definite, yep, that's good, definite integral from 10 to, I think in my thing I said 10.1, didn't I? I shouldn't have said 10.1 down here. It's over a to b, so that should be from 10 to 10.2. So let's go back here. So that would be from 10 to 10.2 of x times 5, so I'll put that in as 5x dx. And there you go. Not surprisingly, that is equal to 10.1. To find the variance in x, from which we can get the standard deviation, and therefore do the standard deviation for the sample, that's going to be equal to e of x squared minus the square of e of x. That's just going to be the definite integral from 10 to 10.2 of x squared times 5, so 5x squared minus, well, we already worked out just above, didn't we, that e of x was equal to 10.1. So let's go back here, let's copy that and just change this to an x squared, and then from that we can subtract 10.1 squared. Alright, so that is, let's go back to here, so 0.003 recurring. So the standard deviation is going to be the square root of that. Let me write that here. So SD of x is going to be the square root of that. Let's go back here. Square root of that number there. 0. Sorry, I'm just writing it down. 577. Yeah, that's all right. And so we can say that e of x bar, well, that's equal to e of x, so it's 10.1, and standard deviation of the mean of these 30 values should be equal to 0.577 divided by the square root of 30, shouldn't it? Because we were told that 30 blocks of cheese were randomly selected, or we're trying to find what the probability if we did select 30 blocks of cheese randomly. So let's go, and maybe we can put this straight into norm CDF, and we're trying to find the probability that, what was it here, that those 30 randomly selected blocks of cheese are greater than. So we're trying to find a probability x bar is greater than 10.12. So we'll say norm CDF 10.12 up to 10.2. I'm going to struggle to fit this in here, aren't I? The mean is 10.1 and the standard deviation is 0.577 over root 30. Let's go and enter that in here. norm CDF of 10.12 up to 10.2. 10.1 is the mean, and the standard deviation is that number divided by the square root of 30. There it is there, 0.02, let's say 0.289. .0289. Alright, so what we've done there is, and I should have made a note here, that we could assume x bar is normal as n is greater than or equal to 30. So it'd be good to make a note of that there.